Shall I start? Otherwise I was going to start with just an apology. Sorry for getting mixed up with this equation yesterday. But F equals 0. Okay? So H is the available horizontal load or resistance. V is the current weight of the pipeline. And V max is the depth to which, or the weight which is pushed the pipeline to the depth that it's actually at the time. Okay, so it's probably the heaviest weight it's seen. It might be a touchdown or when it's been flooded or something. One point to make is that undrained shear strength doesn't appear in that equation, which at first sight might seem a bit strange because that's the strength of the soil, but in reality the depth of embedment is a function of your soil strength. So, and that's what drives the lateral resistance, so it sort of cancels out, if you see what I mean. So, and the other one was this equation, which completely threw me, and I apologise for that. I had literally copied it out of DNV, and it was the first time I'd changed it, and I thought it's the same equation, but that number in the original one was not the current version of DNV. So I thought I'll change it, and I missed that term is not in the equation in the current version of DNV, and it should be there. And if you look at DNV, you'll see it gives you the further up equation B1 actually breaks out F into K naught sine phi, tan phi rather, with submerged unit weight. Which is what I was explaining yesterday. For your purposes, just taking F is, what's the uplift resistance factor, that's fine, and I use that. So, okay, so sorry about that, guys.
Are the updated slides then?
Yeah, Young Chang's got a copy of those slides, and they're on Blackboard if you download them again. Right. Today, the exciting subject of foundations, what they are, what they do. We're only really going in any details. Subsea structures is where we're looking at, but subsea structures for supporting pipeline end manifolds, valve housings, etc., things like that. They also anchoring of floating solutions, which I'll talk about, because any project you're on will probably have either a platform or some sort of FPSO. And then the other important area for foundation solutions, or a variation on foundation solutions, is anchors to actually hold the pipeline as you start your lay. So at the start of S lay or J lay, you need an anchor of some description, simply to hold it back on the seabed. Notes. particular considerations with foundations are variability in seabed soils. Been through that. You do have some interesting ones, particularly carbonate sands and rocks, not just rocks, but you do those. They're particularly interesting, and I'll explain a little bit more about those. I'll give you some case examples there. One of the things I enjoy about offshore foundation design is if you're working onshore, you design a building like this, it's basically a vertical load. You've got no real horizontal load on any structure. Maybe on bridges you might have to consider horizontal loading and so on. With subsea structures, there's always a big component of horizontal loading, and sometimes, in fact often, that is the driving load case, and you've got to work out how you're going to achieve that lateral resistance combined with your vertical capacity. The other thing which you don't really consider very much in onshore structures is cyclic loading. Now that cyclic loading can be a function of pipeline expansion, contraction, but more commonly it's wave loading, and you get a very large number of cycles. I'm not going to go into it in detail because you've got some fancy charts which are look a bit mind-boggling when you see them, but they are there to help. And the other main difference with subsea structures is we land it on the seabed, but we very rarely get the opportunity to prepare a nice flat area for it. You've got to either survey it and satisfy yourself it is sufficiently flat, or you might put rock dump down to level it off, or you design a system which penetrates into the seabed in some way and reduces the need for preparation. There's three main types of foundation, and pretty well all seabed offshore structures fall into one of those categories. Gravity base, the big advantage of that, it's also called mud mats, is you basically land your structure on the seabed and that's it, done. So it's obviously much quicker, it's easy to install, it's low cost. The big disadvantage is the actual capacity is limited, particularly on soft clays. Your vertical capacity and your horizontal capacity is limited. On harder seabed soils, the lateral capacity of the foundation is essentially a function of the weight of the structure, friction angle. So if you don't have enough weight, it slides. And you can engineer that fairly easily, but you do need to put weight in to achieve lateral resistance. Piled foundations are common, and they often are used to help achieve a required lateral resistance. Yeah.
Sorry, you mentioned the friction angle. Now, is it that when the friction angle is small or when it's large that it will slide?
If you've got a high friction angle, it's less likely to slide. Just more friction, basically. But it's also a function of the weight. You know, it's the weight times the tangent of the friction angle gives you the sliding resistance. Okay. Piled structures, they do give you more vertical capacity, they do give you much higher lateral capacity, but you still often have to land the structure on the seabed and then you put the piles in. You don't land the structure on the piles. So you still have a gravity base to design. I'll explain it a bit more as I say. And then suction piles, says they're most suited to soft clays. They are. But they are you can use them in stiffer soils, and there's been a bit of research recently which says that is giving people more confidence in that. but you tend to find them still mainly on deep water soft clay projects. And I've got a bit of a case study for you for that. And as I said, well, as it says, ideal for deep water developments. These are some of the sort of solutions you might see. I mean, I know it's focused really on structures which actually come through the water column, but it's applicable anyway, and it's good background. If you start at this end, that's basically a monopile, a steel tube hammered into the seabed, and this small platform put on it, which will just have a compressor station or something like that, and some control system. It would be normally unmanned. It wouldn't be big enough to be a manned position. Jackups, that's a version of a jackup which is actually designed for with oil storage at the bottom. A more common jackup would be a drilling jackup, which I'm not going to talk about here. But they land them on the seabed and push them in a little bit with preload, and that gives you horizontal capacity. It's a form of gravity base in effect. That's all that is. And a steel jacket is probably the most common sort of structure that you will see on an oil platform. They are landed on basically just the lattices. That section is landed on the seabed, and then it's piled down into the seabed. There's some guide tubes to pile it down, and the piles are grouted or swaged into the guides at the completion of driving, and then you put the top sides on. Just to give you an impression of scale, that's the British Telecom Tower in London, which is one of the tallest buildings in London. I don't think it is now, but it was a few years ago. The concrete gravity platforms are huge. The trawl is in 350 metres of water depth, so the whole platform's the concrete section is over 400 metres high, and I think it was the biggest structure ever to be moved by man, and it is huge. But it's got skirts on it around the sides of the storage tanks that go 25 metres into the seabed. Now, you're not going to get 25 metres with a small structure. But that helps give it lateral capacity, so you push them in, and that gives you immediate lateral capacity, which is what you need. And then you come to floating solutions, which don't actually sit on the seabed, but are anchored to the seabed in some shape or form. And that's what, where on deep water developments you're most likely to find suction piles, as well as supporting seabed structures. In shallower jobs where, as I've said, the geology tends to be harder, you're more likely to have a driven pile solution, so just a tubular steel pile driven into the seabed with a mooring chain on it, and that stops the platform floating production unit, the ship basically drifting off station. Partial factors is just something I want to mention. That they're from DNV, which is the code we tend to use most of the time. It is slowly being supplanted by ISO 19901, but fairly slowly. And if I'm honest, the factors of safety are about the same. Then there's not a big difference in them. So G is your permanent load or dead load. Q is your live load. Usually the live load is often relatively small, and E is your environmental load. So if you factor up your dead loads, you don't have to assume the worst case environmental loading. However, there's another load combination which does take the worst case environmental load, but you don't have to factor it up. It works out at a global factor of safety of between 1.56 and 1.69, depending on whether it's an effective stress analysis or a total stress analysis. For clay soils, we'll always really just be considering the undrained shear strength of the clay. And you need to check settlement. Sometimes that can be important. Particularly soft clay jobs where you've got very soft clay, they're quite a heavy structure, particularly if it's on a gravity base, they can settle and that can affect your pipelines coming in. So what's a gravity base? Basically just a steel plate often. That's pretty much all it is. In sands particularly, the weight can provide the frictional resistance. I've said that really. What we can do to enhance the sliding resistance is put some steel plates around the periphery of the structure, which actually we use the weight of the structure to push those plates into the seabed, and that gives us increased sliding capacity. And if it's a tieback anchor, we still use the sort of standard codes. Okay, so if in this case that's drawing the sort of tieback anchor where you've got your line tension and you're relying on the weight there, and your shear at that interface is giving you your sliding resistance plus a little bit for the skirts there. Okay, that's an example of a mud mat foundation. That was a manifold we did, and it grew arms and legs. I think it went from 40 tons to 80 tons, and getting that to work on soft clay was really quite a challenge. Obviously that's the underside, and what the structural engineers often do is use the skirts on the underside to actually give it rigidity as well, so they're serving a dual purpose of penetrating the seabed, increasing the sliding resistance, and also making the structure rigid. One thing to watch though is if you do that, when you land it on the seabed, there's water inside those skirt compartments, so you have to have holes to let the water out. And I have seen people ignore that, and then on a sort of 2-degree slope somebody had a structure which slid off about 100 yards before it stopped, and they wondered why.
If it's a really soft mud, would that extrude up through the dewatering holes?
You make the holes about 10-15% of the area. Usually they're about 100-150 millimetre diameter on a sort of half metre or more spacing. If you did put many holes in, then yes, there is that potential. But does it really happen? Not really, you know. I've never seen it happen. There are some people do design a grillage foundation which is designed to penetrate to a depth in the seabed. That can have some advantages, particularly when you're lowering it through the water column, because one of the problems with these things is if it's going down horizontally, it's got a huge hydrodynamic drag. Or, you know, if the vessel's moving at all, it's trying to go up and down, so if you don't have a heave compensated crane, it's a real problem. So there is holes cut in that one, but because it was an end termination, that's the pipeline there, that bit there, that's a crane behind it, but there's the end of the pipeline. It actually sort of came down and went down like that, if you like. So it wasn't so bad. But the settlement on that one was a big issue. We had a bit of a bun fight about it. What we got there. Oh, that's another story. Telling surveyors they've got their tidal correction wrong. That's a failure envelope for a mud mat on clay. And what you basically have is you design the size of the mud mat, and you that's the ultimate bearing capacity at a, or factored in this case because it's factored load, factored mud mat. It's a function of the physical size of the mud mat, okay? I have given Yongshan a copy of the sort of 4 pages from DNV which covers the sort of basic design of mud mat foundations, and that will be on Blackboard. It should be there, yeah. If we get a chance, I might do a little bit of a worked example at the end. We'll see how we get on. Now, if that's right at the limit of the vertical capacity, what you find is you can't actually take the full sliding resistance. You get no real sliding resistance from that point. What this line here is the ultimate sliding resistance. And in soft clays, or in clays, that line is actually the area of the mud mat times the undrained shear strength of the seabed soil. So you're assuming full adhesion between the mud mat and the seabed, okay? That doesn't include any allowance for skirts, which may increase it a little bit. What I would caution is you don't want to design a structure which is down there, because you don't have any weight in the structure to actually sort of generate that thing. And it comes back to what I was saying yesterday, that you want clays can ultimately behave in a drain fashion, so you want a certain angle of friction to be developed to ensure that you do make your structure stable. So I know that looks quite shallow, but if that's 50, so that, over there is about 45 degrees. In reality, it's that would be quite safe. The horizontal load is 33, say, but the actual weight on the structure there is 70. So you've got a factor of safety of 2 on the slide, or a coefficient of friction of greater than 0.5. So you'd be okay with that. There is in the codes as well a slight thing that if you've got a rough base on the underside, you can increase the capacity a little bit to do with the way the shear planes move. But don't worry about that, it's a small point. Sands, you get the same sort of thing, that you tend to get a much higher capacity out of sands than you do out of clay soils in terms of vertical capacity. But you still get that reduction with increasing horizontal load or applied horizontal load on the structure. What you do get in sands is a very clear cut-off. So, that's say 50 there. Your ultimate capacity is just over 25. That's a friction angle or a coefficient of the friction of about 0.5, which feels about right to me. Coefficients of friction will be around 0.4, 0.5 sand, steel. Or friction angle of sand is, say 30 to 40 degrees, so it's about right. Okay, but you do have, the code does actually require that you take that into account on a sand seabed. Now if we go on to piled foundations, subsea structures, they're usually landed on the seabed, as I said, and then they're piled into the seabed. And what we do is place pile guides on the structure, so you actually land the structure on the seabed, lower the pile into the guides, and hammer the pile to depth. If you have a subsea manifold, then you usually have 4 piles, 1 in each corner. That's just the standard practice. In theory, I think you could probably do it often with 2 piles, say, but I've never seen anybody actually do that. And then jacket structures, they can have a lot more piles. Again, generally in each corner. Sometimes they might have 6 legs, 6 main legs, and you have a series of piles at each leg, but 4 to 8 piles in each one. And there's an example of a structure this is actually subsea 7, do what they call bundles, and that must be the end bundle, the landward bundle. Manifold. They actually float them out, but they're buoyancy tanks. There's one on the other side as well. That's the mud map there that you can just see going along there. And the way they actually do those is to have a structure at one end, a bundle which includes all the pipeline, water injection line, and an umbilical all wrapped up together. And they have a railway line going inshore, and they just pull it off with the vessel, sort of float it out, and then sink it all down onto the seabed. And it works well for anything up to 7 kilometres. It means there's less offshore time required in commissioning. You can see the pile guide, and that white thing at the top, you can see is just a guide for the piles to be stabbed into. So they crane the pile down and lower it into that guide and then hammer it home. When we did this a few years ago now, it was on quite soft clay. So what we had to do was sort of work out how much they could flood the tanks by, so that the structure was stable on the seabed before it was piled, allowed for the weight of the pile hitting the corner, and then piled it in, and then grouted the piles in place, and then they could flood the tanks properly, or I think they actually take them off, but then they had enough weight support to actually not worry about the structure sinking into the soft clays. And so it was a balancing act, which is what I'm saying. Getting the mud mats right for the structure can be difficult on soft clays because you've got a limited capacity. But once it's piled, it's fine. And ultimately the real reason for putting piles in on that structure was to allow for fishing gear loads, snag of fishing gear, So the design process is essentially check the stability of the mud mats, design the piles using the knowledge of the soil's depth at the requirement. One point I didn't make was that another advantage of a small gravity-based type structure is you just need to know something about the soils really in the top 5 metres. You're not too concerned about what the soils are doing at depth. And if you remember, I said, in the lectures last year, site investigation, you can seabed CPT, Vibracora, quite efficient to do. If you're going to drive piles, you really need to know what's down, and the piles will be, say, 15 to 30 metres depth for a structure like that one I showed you. I think the ones we did there were about 25 metres long. So you need to do a borehole, which is another vessel going to do the survey. So that adds again to the cost of the structure. You consider both vertical and lateral loading conditions, and one of the interesting things about pile design is you tend to design for a vertical capacity, and then you check it's okay for horizontal capacity, but you don't really put the two together in the way that you do with a gravity-based foundation. As I've said, you've got to allow for both those two load components, and as I'll show later on, the same sort of thing for a suction pile. You've also got to check you can drive the piles, and that's another challenge. The piles, by the way, certainly in the UK, Norway, are nearly always 24-inch diameter and 1-inch wall thickness. That's pretty much standard. Yeah. Every job I've worked on in offshore engineering, a pile has been a tubular steel pile. There's no reason why you can't use other things, but everybody uses tubular steel piles. They're easier in some ways to position in a round guide. A round peg in a round guide is easier than a square peg in a square guide. Design methodology, in reality API, DNV and ISO are pretty much the same. Certainly for lateral loading. There's been some developments in vertical loading which I'll come on to, which are repeated in from API to the ISO codes, but they're not in the DNV codes. And to get it actually fixed into the structure, we grout pumps a cementitious grout into the annulus between the guide and the pile itself. Or a quicker way but more expensive way of doing it is to actually swage them. You have basically a hydraulic tool which you lower into the pile and you expand it out over, and it pushes, just plastically deforms the pile into the guide on the structure, and that locks it in place. It's quick, but the cost of the actual swaging tool is expensive, so it's not always the preferred option. Pile vertical capacity is a function of friction on the outside of the pile and the inside of the pile. So if you've got a tubular steel pile, you're getting the friction on the outside but also on the inside of the soil, and actually that usually is the biggest component because the end bearing is quite small. At some point though, as your pile length increases, this area inside the pile is increasing and generating more and more friction. And then at some point you get that the whole soil within the pile moves in theory with the pile. If the pile was to move downwards, that whole soil plug would move. So then your capacity becomes the end resistance over there plus just the outside friction. Not you then start to ignore the inside friction. It's actually quite rare that piles are truly plugged, and certainly when you're driving them, they're very rarely plugged because you're hammering it in. You basically hammer it in, and that shock wave goes down. The inertia of the plug of soil inside the pile means that it effectively stays where it is. So when you hammer the pile in, you've got to be quite careful that you allow for some of that soil is actually displaced in over, so you end up with more soil inside or the soil in the pile actually comes up over, and you've got to allow for that when you're working out your how much pile you have left to stick up, or where your follower is, which is what you put on top of the pile to put the hammer on. As I said, there have been a lot of new methods published in the last few years for pile design. The API main text method, I don't know, have you used API at all? You've got the main text, and then you've got a commentary which sort of provides a little bit more background and so on. The main text method is still the old method, so don't use that. It's not very good. It's easier to use, and it's good enough for a quick feel to sort of get an idea of what you're doing, but particularly in some sands, very dense sands and very loose sands, it's not reliable. And the API actually say at the start, we don't recommend you use these methods, but here they are. The other thing to be aware of if you're ever working in carbonate soils, you know, sort of in the Middle East or northwest shelf of Australia, carbonate sands are can crush if they're sort of skeletal remains, often of shells, something like that. They crush. Now that led to a lot of research work in the early 90s, I think it was. In Australia, they built the Rankin platform, and the piles, I think, were about 100 metres long. And by all accounts, they stuck the hammer on the top of the pile, and at the first blow, both the pile and the hammer had disappeared into the seabed. Okay. So they did a lot of work. Oh, what are we going to do about this? The answer is that what they did was to grout it. In that case, they pump grout, and that gets around the loss of friction due to crushing of the sand grains. When the sand grains crush, you don't get that sort of horizontal stress, which is generating the friction against the pile wall. Well, we know all about this now. So then a few years later, a few miles away, they put the Goodwin platform, and they knew there was some limestone bands there. So they did that. They started hammering, and yes, they got it about right. They didn't hammer it too hard, so the pile didn't disappear into the seabed. But they reduced the wall thickness so much that when the pile hit the limestone bands, it deformed. And so they had another problem.
Because of the acidic nature.
It's just the strength of it. There's some guidance in API on minimum wall thickness for a pile based on the diameter. It's still quite thin wall, but it's something you do need to think about. That if you make the pile wall too thin, it may not have the structural strength to sort of overcome or any sort of hard band or layer which might be present. A classic one is boulders. Say, the boulders can be there, and you drive a pile and it starts to deflect. Sorry? Yep.
With, not talking about the carbonate, just with normal mud or whatever, if you're piling with an undersized hammer, would that increase the risk of plugging it?
No, it doesn't really increase the risk of plugging it. If you're using an undersized hammer, your main risk is the fatigue life of the pile.
Okay.
That you put so many blows in that you fatigue it, basically. If you use a bigger hammer, I mean, you can overstress the pile. It is a balance to hit.
Yeah.
And I have seen some piles, where that becomes the criteria. It tends to be with longer piles. But yeah, you do have to consider it, the fatigue life, and the size of hammer you use. Yeah, so if we talk about pile capacity,
Yeah, well, that's at commissioning. Do we have any considerations for these piles at decommissioning?
Decommissioning. Yeah, usually what they try and do is cut them below the seabed and just leave the rest in. That's one of the times where the volume of soil in the pile becomes an issue, because some people, particularly for mooring piles, in theory you can drive them below the seabed, and your mooring chain is often at sort of 5-6 metres, is on a pad 5 or 6 metres below the seabed, and the top of the pile doesn't actually do much. So in theory you only do that, but then you find the follower, which is usually plugged into the pile, gets full of soil around it, and then you can't get the follower out. So you end up with a bit of a problem, really. So it's it's easier to leave it sort of half a metre above seabed level, and then at decommissioning cut it off, which is sometimes done explosively. That's a common way of doing it. Yeah, so in clay, and this is essentially based on the main text method of API, which is a gross simplification, as I say. You really want, if you're doing permanent works design, you want to be doing doing one of the more advanced methods, but it gives you a feel and it's a quick calculation. 9 times the undrained shear strength times the area of the wall of the pile, usually. It may be plugged, so you need to consider that. Then side friction, they recommend for over-consolidated clays, it should not exceed 48 kPa, 1 kips per square foot, which is why it's a funny number. Lower plasticity clays, it might equal the undrained shear strength. So in soft clays, essentially, you'll mobilise the full strength of the clay at the wall, at the interface friction. But I do recommend you look at ISO, and you can get ISO through the university as well if you want to, but it's a great long thing. I wouldn't ask a question on that, don't worry. For sands, it's a similar process of calculating the end bearing and the side friction, and with some factors. Beta is dimensionless skin friction pattern, P naught is effective overburden pressure, so that's the weight of the soil. So if you're 10 metres down and the submerged unit weight of the soil is 10 kilonewtons per cubic metre, your effective overburden pressure is 100 kilonewtons per metre squared. Okay. Again, end bearing, similar sort of equation. That's per unit area. They're both per unit area, so you'd have to allow for the unit area. Dimensionless bearing capacity factor is P naught dash times P naught dash gives you the end bearing capacity. API give you some nice little numbers to give you a start as to what values might be appropriate. So there's your skin friction and your end bearing. In both cases, there's a limiting value. So as you go deeper and deeper, your overburden stress increases. But at some point, the code says you've got to stop increasing it. So that there's a limited benefit by going deeper and deeper. It's still a benefit because you're increasing the surface area, but there's a caveat there which needs to be taken into account. Okay, that is quite a useful table, and you can certainly do a first pass pile design on that, and that's again that's useful if you're just costing up a job or getting a feel for how deep a borehole needs to be. But as I say, I would recommend that that's just a first pass, and detailed design uses one of the commentary methods in API. Yeah, this is really just going on to the commentary methods and saying there are now 4 methods in ISO in the appendix. There was a lot of work done by Richard Jardine and Shell. But it was one of those academic things where everybody thought, oh, they've done that, we'll have our own system. So you've got the simplified one from Imperial College, UWA's University of Western Australia, Fugro are the sort of biggest survey contractor in the world, and NGI is Norwegian Geotechnical Institute. To be fair, they're all more reliable than the main text method, and they're all sort of generally not that much different. They're within 10-20% of each other. Whereas in some cases, if you go to the main text methods, it can be 30-40% some particular soils. Yeah, that's the sort of equation you get in the, and that's why it gets a bit more fiddly to use. You need more parameters, a better estimate of what they are, and it's a longer-winded equation, so it's not as simple and easy to use as the sort of main text method. Okay, I wouldn't lose too much sleep over that, don't worry. Now we come to one of the reasons for piling is often to achieve an increased lateral load and or a lateral capacity from the structure, and we have two main scenarios, if you like, long piles and short piles, and within each of those, if you've got if your head is free to rotate, then it's a free-headed pile. You can see the bottom of the pile is essentially fairly stable, or if it's fixed head, the pile can't rotate in the same way. It's in a structure, if it's a four-pile structure, the pile can't rotate. But in that case, it's a long pile. Then you could have a short pile as well. I know you're not doing renewables, but if you're a wind farm monopile, there as an example is a good example of a short pile, and they tend to be about 6 meters diameter and 30 meters long. That would be a short pile. Okay. And they can either translate laterally if they're fixed, which is quite rare for that sort of scenario. It would be a small structure with four piles. Any single pile, monopile type solution would be free-headed, so it would rotate in effect. Now, what we can't do is do an easy analysis to work out the displacement criteria of a pile. It's got to be you've got a non-linear soil response from the pile loading the soil. When it loads it up, it doesn't displace the soil in a linear fashion. It's not pure a single value. And we've also got to take into account the stiffness of the pile. So as the pile moves, it's also bending, and it's also a non-linear response from the soil. So we don't do it by hand, we do it with a computer. So much easier. You plug a number in and you get an answer out. And you can do a fag packet calculation for ultimate capacity, but the actual displacement, most laterally loaded piles are actually driven by displacement criteria. You use a computer to calculate it. Now we have what are called PY curves, which model the response of the soil, and they're curves like this, where if you just take the case of a static pile, then when you load it up initially, the response is quite stiff. It doesn't move that far. But as you increase the load, the soil starts to behave plastically around the pile, and it starts to yield more easily, and at some point, at some load, the pile will just move continuously through the soil for no increase in load. A bit like, if you're cutting steel, it has a certain shear value, and it'll shear at that point, and something would pass through it. That applies to both sands and clays as well, a similar form of PY curve. You do get a little bit more complicated in the codes. You might allow for cyclic resistance, which reduces it. It's a bit of an exaggeration there, because that's 0.72, that distance there, so it's a bit exaggerated. You get that response, and ultimately, if it's cycling backwards and forwards, you find that the pile actually makes a bigger hole. So you get a response like that, where there's a gap around the top of the pile. That's more of a concern for things which are experiencing a very large number of significant loads. And we can build that curve up using this sort of table. That one's actually from API, or ISO rather, I think. And you just build it up basically, and you essentially plug the numbers into the computer based on that equation YC, which is the ultimate, the current displacement given the stiffness of the pile. That's epsilon C, and epsilon C there is half the deviator stress of the clay in a lab test, or epsilon 50. We actually read it out of a book most of the time, depending on the strength of the soil. But it's numbers you just plug into a computer, and then we calculate the lateral load response to the pile. And the sort of curves you get, this is for a pile which actually comes quite some way above the seabed, and I think it was loaded there. That's the displacement analysis, so you can see that most of the displacement is occurring close to mudline. The bending moment is always a maximum just below mudline. If you've got a laterally loaded pile, the load is obviously generally applied above mudline. And shear, and that basically, when you've got all the analysis correct, you press a button and you get that graph. But it is an iterative process because you've got to check your stress in the pile from the bending moment to say, okay, the pile has the capacity to withstand that bending moment, and as you make the pile stiffer, you'll change that curve. So the response will change as the pile becomes stiffer or less stiff. Okay? All right with that? Pile installation. I've explained how if you've got a seabed structure, you have guides in the corners to support the pile as it's driven. If you have a mooring pile, or it might be a startup pile for a pipe lay operation, then you can't use a single pile easily. It's got to be supported at the start of driving, and you can use a frame like this. There's a couple of companies have them. They're basically, it's a guide there, a steel tube, and you lower the pile into it, and at some point, so you can drive the pile to the seabed, that frame opens out. But it's another example of where you've got to have a knowledge of gravity or understanding of gravity bases, because when you land those on the seabed, they're a gravity base. And there's a wide range of hammers. Basically, Menck and IHC build the hammers. They're pretty much the only two people who supply hammers. And IHC are the bigger company. They make more hammers. A pretty standard one now is an S200, and that'll drive you 24-inch piles pretty happily. Whereas Menck tend to do more of the big hammers, the really big ones. Comes back, somebody made the point about driving the piles, and you do have to do a driving analysis. You've got to choose the right sized hammer for the job. We basically calculate a static resistance to driving, which in some ways is very similar to working out the axial capacity of the pile. Work it out and work out the resistance at depth as it goes down. We'll estimate analyse whether the pile is plugged or unplugged, although in reality in most cases it behaves in an unplugged fashion for driving. And it's another case of where you really don't want to do the calculation by hand. You want to do it with a program. And GRL REAP is the industry standard. And basically you calculate the compression wave going down the pile and how that responds to the soil, and then how far you drive it on each blow. And you select a hammer, try and drive it, make sure your blow count's all right, and if your hammer's not big enough, then or you've got too many blows, you go back and reanalyze it, and until you get to the right sized hammer. Mainly, the client will tell you, that's the hammer I want to use, can I use it? And if you can't use it, you've usually got to try and find a way of making it work, if you like, or find the cost. And the cost can be quite significant, because I've been involved in one case where the pile, I think it was oversized, but they had an analysis done by somebody who came up with a big hammer, unrealistically big, but that had an impact on the crane. They couldn't use the crane, they had to get another boat with a different crane to lift the hammer, and it was really a case that if you'd selected the right hammer in the first place, it would have been a lot more cost effective, but because somebody had said it might be this size hammer that you really need, they grossly over designed the pile hammer, but then everybody was frightened to go away from that because, oh, what if it doesn't drive? And it was, lack of competence really from the original site investigation contractor. So what we do is work out the strength profile effectively, calculate the static resistance to driving, plug it into WEEP, or there's one or two other programs, and then we estimate usually a best estimate for the driving resistance and an upper bound driving analysis to see how well the pile's got in effect. I don't actually have that analysis from the actual pile driving, because it's often quite difficult to get them. People don't automatically give them to you. But I did pull that one down, which is another example of an actual pile driving in our results. So that's the blow count in every 30 centimetres, and that's the penetration. So you can see here what they've probably done is driven to 20 metres, and then because it's a fairly long pile, they've had to weld on another section, so they've stopped. And what happens when you stop driving is that the soil consolidates around the pile a little bit and recovers some of its strength a little bit, like I was saying yesterday around pipelines. You get an excess pore pressure generated, it dissipates, and the clay particularly recovers its strength. So you've got to hit it harder to get it started, and that is quite an important one, particularly as you see here. It's taken really quite a lot of blows to get it started, and that can impact on your fatigue life as well if you're not careful. But once it's started going, look how far it's come down, 1/6 of the blow count. So it's that sort of thing, you need to be aware of. I mean, I think for yourselves, your pipeline engineers mainly, but you're going to come across it and people are going to ask that question. At least you'll hopefully understand why it might be an issue.
Can you vibrate the end of the pile? If it refuses, can you vibrate the pile to...
Yeah, vibration works best in sands.
Okay.
It's sorry. It's not so effective in clays, and you can actually vibrate a pile into sands, but most hammers are impact hammers rather than vibratory hammers. I don't know of anybody who's using a vibratory hammer on a regular basis.
Oh, I mean, just to try and get over a refusal and then carry on with stuff like that.
Yeah, it's a different hammer, that's the trouble. And they're not little things. Really? Yes, money and the craneage time. You've got to, if you pick one up and put it on the pile to get it started, you've got to come back and then put the other hammer back on, and so usually go with one hammer. What I'm going to do now is talk a little bit about suction piles, a little bit of a case study. That's a suction pile. You can see that's actually the pad eye there, and that's a mooring line to be hooked up when it's landed on the seabed. You can That section of the pile has not been painted. It never is. They only did it once. They painted the whole pile and they found that it went in much more easily. That's obviously on its side. And then they didn't get the vertical because it was a mooring line. There's an uplift force from the mooring line. I was trying to pull it out and they ended up putting a lot of lead on top of the pile, called it in the seabed. So nobody ever paints the embedded section of a suction pile now. And if you do, ask them why. Because it's one of those sort of stories. It's like the ranking platform that I mentioned before. Everybody knows about it. Nobody is going to get caught like that again. Those big valves there, or flaps, are important because when you land the pile on the seabed, it's open at the other end. So you've got a lot of water to get out. A bit like the holes on a mud mat. That water's got to get out of from inside that compartment. But once it's into the seabed, you want to actually suck it in, okay? I'll go through the installation process a little bit later. That would be about 5 meters diameter as well. That's a fairly typical diameter for a suction pile and about 15 meters long. If you're working in West Africa, 15 meters by 5 is a good start for your mooring piles. Why would we use suction piles? Well, particularly on deep water jobs, a driven pile needs a lot of power to the hammer to make it work, to drive it into the seabed. With a suction pile, a little pump will pump the water out and actually pull the pile into the seabed. So you can run it from an ROV, basically, a conventional ROV, and ROVs are 10 a penny. Big hammers, especially deep water hammers, there's a handful in the world, if that. So that's a big difference, a big reason for using suction piles. So they're quicker and often simpler to install. You know, when you land them on the seabed and they sink in enough under self-weight to be stable. Not like a driven pile where you might have to use one of those frames I showed before. And that all reduces your vessel installation time as well. It's probably the biggest cost. So this is a job we did a few years ago now, but offshore Nigeria, and the Gulf of Guinea, and that was the field layout. So you've got in fairly typical field layout, an FPSO there, mooring piles there, mooring lines there, 2 drill centres, and that was an offloading buoy there with 3 sets of mooring lines there. What I talk about now is really mainly related to the mooring piles. So it was an interesting one. That's an image of the seabed. The vertical scale is exaggerated because that trough through there is only a few meters deep, but it was there and noticeable, and it's probably been caused by a turbidite flow or something like that, carving a channel down the thing. 2 drill centres there and there. That's from the Digi-survey, the digital survey they call it. You can see the structure of the seabed soils there. It's more of a geological thing here to about what the channel features are, and all that sort of stuff, which, to be honest, is a bit beyond our interest because we're really interested in this top bit here. But if we look at that chart, you can see this is a cone penetration test. So the red line is the cone tip resistance. They've taken samples, that's the borehole log, and you can see their index tests, their plasticity indices. So that's the plastic limit, the liquid limit, and then some of the other ones. You can't really see them all up here, they'll all be up here. It was very soft clay. The moisture content was close to the liquid limit, in some cases actually greater than the liquid limit. And their undrained shear strength test, so that's the undrained shear strength there. That's a remoulded strength, the empty ones are remoulded samples. 2 soil units were picked up from that horizon. It's the best print I've got, I'm afraid, but it shows the, the geologist has interpreted a horizon. There in 2 soil units. The unit A was a nice clean soft clay with very few sandbands or anything in it. But you can see here there's some spikes in the cone tip resistance which are associated with sandbands. And one of the concerns at the time was that we didn't want the piles to go too close to those sandbands, because what can happen is as you suck the pile in, the clay can actually be sucked into the pile and water come in through the sand underneath it, and then you don't get the pile in to depth. In reality, I think that was probably a bit of an overly cautious approach, but it was when suction piles were still fairly new. And we did a full geotechnical survey, all the usual stuff there, and for that sort of development you do some quite advanced testing, like DSS is direct simple shear, where you put a little sample of soil like that. This always amazes me. It's literally 60 millimeters square by 19 millimeters high, I think, in a machine which is like that. And you put a thick rubber membrane on the outside and allow for that, and you've got this really soft clay, and you work out the strength from that, and by shearing it horizontally. There's nothing simple about direct simple shear when you're actually doing the tests, but you get good quality results from it, to be fair. And you know, the routine stuff, the soils have slightly different strengths in extension, direct shear, and compression is in triaxial, so we allow for that. And thixotropy is to do with the recovery of strength with time. So, you know, what I've talked about, understanding how that works is an important part of the design process. And we also did some cyclic tests as well to understand how the strength of the clay changed with number of load cycles that it experienced. Obviously, if you're going to do all this, you want good quality testing. You want to make sure they're going to be as reliable as possible. So the testing was actually done by in Norway by the Norwegian Geotechnical Institute. But what they do is they take their sample cores along to the veterinary college, and they do a CAT scan of them. So you can see here the layering in the soil. Those are the end caps in the sample tube, and that actually is is the sort of sample split, if you like, just to make it look better. But you can see you don't really want to take that part of the sample because there's water or something's happened there. You'd be much happier taking that or that section of the sample to do your testing on, so you've got really undisturbed clay, truly undisturbed clay. And you get much more reliable results, obviously, if you've got undisturbed material. The comment there about confining pressure is released. That's the water pressure, because this is in about 1,300 metres of water. So if you've got any gas in the soil, or what might not be gas at 1,300 metres, what's that? 30 newtons per millimetre squared external pressure, water pressure, will be gas when you've only got 10 kilonewtons per metre squared of air pressure. You can easily change it, so that's why you might get some of those, that fissuring in the clay. And went through the process of reviewing all the results, understanding everything, determining how the direct simple shear would be, etc. And that's the sort of consistency you get in a lot of deep water projects, where you get this quite narrow band of cone test data all falling together. And you can see about this level here how the geology's become more disrupted and more sand lenses, and that's what we wanted to avoid. Submerged unit weight, it increases slightly with depth because the weight of overlying soil has squeezed more water out as you go deeper. And then we came up with some design lines. Can you see that? Yeah, the design lines just in there. These results are the lab test results, and you've got to show them. But it is one of the dangers if you're doing quick tests on the back deck on a sample of soil. You put a toe vein in, and it's a really crude test. You get a low value of what you expect, but then you're sort of trying to explain it away to the client. You're saying, why have you done those? Or the verification body's the worst one. We've got strengths of that. Why haven't you allowed for them in design? Well, they were cheap tests. They were just crude and they're not very reliable. Well, okay. The moulded strength, it shows again just how much it's come down. If you look, that's, see if that's 20 kPa there, so at say 12 meters depth, 12 to 15 meters depth, you can see there that at 12 to 15 meters depth the strength is probably slightly more than halved when it's been remoulded, and from CPT data that is, and even more so when you look at the lab test data. So the process you go through with design is to do an initial analysis, limit equilibrium, or plastic work type analysis, and then we usually do a finite element analysis, a 3D finite element analysis. That gives us the size of the suction pile, and then we have to calculate the penetration resistance, and you end up in a bit of an iterative loop with the structural engineers, because if you design the pile to a size, you estimate a wall thickness, the weight of the steel based on the wall thickness will drive it in a certain depth. As you make the pile lighter and the wall thickness thinner, it doesn't go in as deeply, but then you need more pressure to actually suck it in, so you need to go back to the structural engineer and say, well, is that wall thickness acceptable to support the pressure differential? Some of the other issues are you usually allow, sorry about the formatting there, setup is an extraction after 7 days, so you basically you can put it in and then you can pump water into the pile and push it out. If it hasn't gone in straight for some reason, you can reposition it. You've got 7 days to decide whether you need to do that, whether you can live with it where it is. And the other thing is, at some point it's going to be used, but the soil is reconsolidating, the thixotropy is coming into play. So you've got a time period till it recovers that strength and gains enough strength to actually hold the FPSO in position. And creep and cyclic behaviour. Oh, sorry. Sorry. Creep's mainly important for the pile gradually being pulled out, particularly if you've got a taut line mooring coming straight up to the vessel. You've got quite a big uplift component. Cyclic behaviour, every time a wave goes past, it's a cycle of load. Small with a most waves almost insignificant, but when you've got a 100-year storm, that's when it starts to become much more significant. Choose I'll quote this one. What we do want the pile to do is, or the way we analyse the pile, is we actually almost extend the anchor line from the pad eye back to there, which makes it much easier in terms of analysis, and you've not got an overturning moment from the pile, the pad eye there on the vertical load. By extending it virtually back to the centre of the pile, you move your load to there and the horizontal load down to there, and we want that point of rotation to actually be slightly backwards. I'll show why on the next slide. That is typically around 2/3 the embedded length of the pile, or the depth of the pad eye, for a suction pile. The reason we want the pad eye to be at a certain depth is, in a way, pure lateral translation is the objective, but if we put the pad eye in the wrong place, it starts to rotate forwards, and ultimately, if you have the pad eye at the seabed, at the capacity of the pile will quite literally be between 1/6 and 1/10 of a pile where the pad eye is at depth down here, like this one. Don't want it to just rotate laterally like that, because if it does that, you get a crack at the back of the pile. It can open up and water can flow in there, and because we're relying on the strength of the clay around the pile, the adhesion between the clay and the pile to resist the load pulling it out of the seabed, we really don't want that tension crack to open. So where we're trying to get the pile to be is to rotate slightly backwards. So it's trying to move forwards, but the top is actually coming backwards, and that's ensuring that the tension crack doesn't open up here, and you don't get a tension crack to the same extent there. So you're maintaining your adhesion between the pile wall and the soil around the pile. And that's the preferred location for the pad eye. We do, in the case of a suction pile, allow for the vertical and horizontal capacity. What we basically do is calculate a simple vertical capacity and calculate a pure horizontal capacity and fit a quadratic curve, a cubic quadratic curve between those 2 points, and make sure our applied load in terms of applied horizontal and applied vertical load falls within that envelope. And that sort of gives us a good handle on the physical size of the pile, because what we don't want to be doing too often or too many times is running too many suction finite element analyses for a suction pile. Okay. So the installation process or design is calculate the self-weight penetration of the pile, calculate that the resistance of driving it to depth, and the process is the end bearing resistance and adhesion of the pile. This is exactly the same as with a driven pile. We will check for suction heave in the as the pile goes in. That this is the diagram of the sort of stresses on the pile, the forces. So you've got friction on the inside and outside, and tip resistance. In reality, in a clay soil, that tip resistance is, less than 5% easily of the total resistance to penetration. And by sucking water out there, you actually suck the pile into the seabed. So initially, if you remember when I showed you the picture of the suction pile. You saw the two butterfly valves at the top. They're open. As the pile goes in, all that water's got initially to be displaced, and the pile will probably go in, 2/3 of its total depth, maybe even close to its full penetration, and then pump the water out to get it in that last little bit. And it does work. That's some results of, again, it's the sort of values that are really hard to get hold of, because everybody just, oh yeah, right, that's okay, and nobody actually gives you the results at the end of the day, which would be really interesting. But you can see the predicted, like a pile driving analysis, upper bound, predicted lower bound penetration, and you really want all the piles to sit in that band, because it's giving you confidence that your interpretation of the soils has been correct as well. If if the penetration curve was over here, then you've underestimated the strength of the soil, so you could have made the pile a bit smaller. If it's down here, you've got a bigger problem, because your pile might be under capacity, and then you've got some fast talking to do. That's the trouble with that. What was I going to say? Another thing about suction piles is the suction is used to penetrate the suction pile. The suction is not maintained during the life of the pile. Okay? You switch it off. They leave the top of the pile closed, but if the pile is being pulled upwards all its life, say for a riser base, which the riser is obviously designed to be buoyant and tied down to the seabed, you might use the weight of the pile, and you might allow for some adhesion on the side of the walls of the pile, but you don't allow for suction in the pile. The difference is, if it's a short-term load, like a wave load going past, which is giving a tug up, then you allow for suction at that point. But that suction is only generated by the pile being pulled upwards, okay? And it's only for a short period of time. Now, the reason for that is, if you have you've got those big butterfly valves, you've got another valve for the suction pump to sit on it. If that leaks a little bit over 25 years, that small leak actually becomes a significant amount of water. If it's only, say, a 10-year storm going by for 3 hours, not much water is going to go through that small leak, and you can be reasonably confident about that. Because a 25-year design life, 10-year return period storm, you might have 3 during the life of the pile, so it's not going to be a significant volume of water. So, okay, suction piles are only suction for installation. The other thing to be aware of is tie-back anchors. There's various types available. 2 main categories, and I only talk about high holding power anchors here. A ship anchor is essentially something which is designed to skim over the seabed and just dig. It's not designed to dig to depth. Whereas particularly Stev, Pre, Bruce and Flipper Delta, they are designed to penetrate deeply into the seabed. We can do a crude sort of assessment of the capacity of an anchor, but more, if it's for a permanent mooring, you would want to do something a bit more. So there's some suction piles, anchors. That's a Stev Pre. That's actually lying on its back, so they're the fluke tips that would be penetrated into the seabed. And that's a Flipper Delta. Both of them are designed such that if it's in a soil, the soil will pass through the anchor. So if you look, they're plates, they're thin plates, and give quite a high rigidity, but they've got a big gap in them, so the anchor will actually penetrate deep. The soil will pass through there, and that will pull the anchor into the seabed. The flipper delta, it's a hinged anchor, so that needs to be landed in the correct orientation, otherwise it won't penetrate. Flipper delta, like that, that's that palm there which supports it. The tips drop down onto the seabed, and then when you pull it, the soil can actually flow through there. Whereas if you look at a ship anchor, that's quite solid. The soil, it's designed to actually sit on the soil. The flukes open and then go like that, but then they'd actually drag like that, whereas that type of anchor is designed to go like that. And by doing that, you in a soft clay, this clay is getting stronger as you go deeper, and in the sand, it's gaining its strength from the friction, the overburden pressure, so it's getting much stiffer. An AC14 is really more designed for harder soils. It's not really designed so much to penetrate deeply. You can see the palm there is much heavier. Those are like that to try and penetrate into sand rather than skid over the top of sand. And there's some efficiency factors. That's obviously 30 there and 23 there. But you can see how efficient something like a Stev Pre is. You know, in sand, soft clays, you get 23, 30 times the weight of the anchor as your holding capacity. So a 5-ton anchor, you've got over 100 tons capacity from it, which is pretty good compared to something like an AC14, which is, you know, not that effective in reality in comparison. Okay.
Does the flipper delta and the steep grade, do they have to be retrieved backwards?
You usually just pull them out, go over it, and then by pulling the flukes like that, you're able to pull it up over, in theory.
So they're sort of equivalent, the anchors on the boats.
Yeah, well, an AC14 probably wouldn't penetrate that deeply, which is why it's not really a proper high holding power anchor. Mm-hmm. But you don't get a big efficiency factor from it. Stev Pre's, you can put a line on them and pull them backwards.
Yeah. We've had problems with similar ones. You kind of get them out of the boats, hasn't got enough buoyancy to lift it.
Which ones is that? The flipper delta?
It'd be equivalent to the flipper delta, I suppose.
Yeah, they're quite a popular anchor, the flipper deltas. They're really designed for soft clay, but a lot of people use them in all sorts of ground, and they do work. But they are designed to penetrate fairly deeply. Whereas a ship anchor, the ship wants to be able to get his anchor back. It's much more of a just sort of a brake, if you like, to slow you down rather than to or stop you moving. Whereas that's really designed to hold you on position. So just to summarise, particularly for tie-back anchors for pipe lay, clump weights, simplest option. Been through that. Lowest installation risk and easiest to design and install, but it is sensitive to seabed strength. Pile, you need to drive it into the seabed, but it is reliable. But another disadvantage is you can't get it back out when you've used it. The suction can, they do work well in soft clays, and actually the advantage is you can get them out usually, especially if you designed it as a hold back anchor. And I know some people have, one or two on the shelf, but in the store yard, which they've used on several occasions and moved from job to job, or within a job, to just hold back pipelines when they've been laying them. And then a drag anchor, it's got its disadvantages, as you say. Sometimes if they use the wrong anchor, get it out can be difficult. You also difficult to predict where it's actually going to stop when you hold it, and then if you use a sheave block for your tie back or to pull the pipeline out of the vessel, well, that's difficult because you've got to hold it above the seabed in some way so it doesn't get jammed up with soils. So, I mean, the clump weight is the easiest if you can do it, and also you can put the pad eye easily on it and a little bit above seabed, but you're limited in capacity, really. It's the trouble. What I usually do at this point is just run through the code a little bit, if that's okay with you all. I think I've got it in the stick. I hope I have. I'm not sure that I have actually. Sorry, just give me a minute. No. Right, this is a part of DNV and the section on gravity-based design, and you've got this on Blackboard. It starts with sand, and then there's a section on clay. We'll concentrate on the section on clay because it's a bit easier, but it's the same principle throughout. Where's the section on clay gone? That equation there is the one for clay. First thing to note is if you have a gravity base structure, let's say a clump weight on the seabed there like that, if you put a load there, we'll assume it's horizontal, then your weight acts that way and your T is horizontal. What that means is that your resultant force is like that, okay? So you have an eccentricity in the load application, which is this bit here. So when we do, if we do have that sort of situation where the got a horizontal load above seabed, obviously if it's seabed, then the resultant is through there, so you don't get any eccentricity on the resultant on the base. But we have to allow for that under the code. So if that is B and that is E B dashed is our effective width of the foundation, and that equals B minus 2E. So what we actually do is that becomes the effective width of the foundation if that's 2E. Okay? Just got to allow for that. It's just a sort of structural thing that it's necessary to do. Now, if we look at the equation for clay when I found it, that equation there, QU NCSU plus 1. NC is 5.14, okay? It always is 5.14. It never changes. Well, sometimes you do change it, in effect, with these factors here. So, if you have, well, let's write it out. That doesn't have the area in it, that equation as well, so that's the bearing capacity per unit area, okay? So, then you have the factors. One is obviously just that, and then you go through the various different factors. SCA is a shape factor, which is there. We'll assume at the moment that ICA equals 0.5, okay? It only really changes if you've got a significant area or significant skirts, and we'll ignore skirts at the moment, okay? I think that's right anyway. You do it might change a little, it changes a little bit, but for this purpose we'll just take it as 0.5. So it's that now if you've got as B dashed upon L, sorry, that's yeah. Look at that one. Yeah, that's right, yeah. Right. We look at that one. That's actually, if you look, to do with this section where you've got an increase in shear strength with depth, which is common in soft clays. But for a lot of, once you've got firm clay, that change in strength with depth is probably insignificant. So SCA was 0.2 times, effectively, if ICA is 0.5, that cancels out. Okay? B dashed upon L. Sorry, does it cancel out? Yeah, because it goes to 0. Shouldn't be right. If you've got a square foundation, or the effective area is square, then SCA ends up at 0.2. Okay, it does. That becomes ICA becomes 0. That's what I mean. Yeah. Right. So that then SCA becomes 2. As L increases, that will become smaller. Okay. So it's heading towards 0, which is why under this equation SCA is added. So effectively, if that's SCA there, we've got a square foundation, that becomes 0.2, okay? And dA is a coefficient for the depth of embedment. And the reason you have that in is if you have a structure on the seabed like that, your shear planes are essentially like that. Now that, which is what the NCA value is doing, allowing for the length of those shear planes, because the capacity is effectively a function of that, the length of that plane times the undrained shear strength. If you embed the foundation like that, so that that's your foundation now, your shear plane goes down like that and it becomes longer. So what the DCA value is doing is allowing for the depth of embedment. Okay, if we ignore that, then it equals 0. If we assume most seabed structures are with no skirts, they land on the seabed, no depth of embedment. Okay, so that would in this case that would equal 0 if we're talking about a structure which is not embedded into the seabed. And then ICA equals the value, where is it? ICA is that value which you've said equals 0.5, haven't we? Sorry, 0, because this bit effectively cancels out. Yeah, that becomes FH1 is horizontal force on effective area. A upon SU is area, effective area, times the undrained shear strength. If we're relying on all that being given, then that equation becomes 1, 0.5 times, sorry, I don't know now. Ends up at 0.5, I'm sure. You just work through the sum anyway. ICA becomes 0. Yes, ICA becomes 0 if we're just relying on the structure being on the seabed, okay? And the horizontal stress. So ICA drops out. So actually we end up with a minus ICA, isn't it? We'll say that's 0. And then doesn't look very well, does it? Plus P naught dashed. That allows for that depth of embedment, the surcharge provided as well, so that you're down for the length of the shear planes and the thing. But if you've got structure on the seabed, that drops out, okay? So it really ends up, it's not a difficult equation. It looks harder than it actually is. If we have an infinitely long strip footing, that value, if L becomes large and B becomes relatively small, that equation becomes close to 0. So you end up for an infinitely long footing with an effective NC value of 1 to 5.14 times 1. If you have a square footing, that's when you end up with this effectively 1.2 times NC, which is 5.14, which ends up at 6.14 roughly. And that's, if you look in the books, that's what you get from charts, from just the way DNV do it. So your ultimate bearing capacity per unit area, if we've got, say, a clay of, if SU equals 10 kPa, then Q equals 6.14, because we've got that there, times 10 kPa, which equals 61 kilonewtons per metre squared. Okay? And then you multiply by the area of the base. So if it's a base of, say, 5 metres by 5 metres, that wasn't a very good choice of numbers, was it? 25 times 6 is 150, you know? Sorry, times 60 is 150, 2,500. Oh, that's wrong, isn't it? That's 60. I got the year for some reason. 25 times 60 is 100, that's 150, 1,500 kilonewtons, 150 tons. So that's your capacity. Okay, then your vertical capacity. But if you start applying horizontal load, your ICA changes, you work it through. FH1 stays as basically that divided by that value, which is, say, 50 times 25 times 10, 250 kPa. So it just works through. Okay, and that is the way the equation works. For sands, it's a little bit different in that that long equation there, all this, if you don't have skirts, if you land on the seabed, P0 dashed becomes 0, and A, soil attraction, well, if you think about what I've said, we usually consider sands as purely frictional materials, so you don't have any soil cohesion in a sand, so A becomes 0. So all that part of the equation drops out. And then you're just left with that part of the equation, 0.5 times gamma dash. The main thing is that B dash then appears in the calculation. And then you have an N gamma factor, which is like an NC factor, but you read it off this chart here. And you usually use Brinch-Hansen, this column here, for these purposes, because it's obviously, as you can see, it's a lower value, and usually you're up in this part of the equation here, so you can see how big those numbers get in a sand with a any sort of meaningful friction angle. And then you go through a similar process with these values, except they default to 1, and that's your QU. If you're using a small q, it means it's bearing capacity per unit area. It's not the total capacity of the foundation. You've got to multiply it by the foundation size. Okay? And you just go through that process, and that's it. It's fairly simple and quick. And the I gamma factor takes into account the horizontal load. Okay? Have a look at that, and just there's examples in all the standard soil mechanics textbooks if you want to. Do you get model answers? I do model answers when I do a exam question. Sorry?
For the exam papers we don't get them.
No, do you not? If somebody asks me, I can maybe send you one or two through.
That'd be good,
Yeah. Okay. I don't know why they don't give you model answers, because we've got to do them for the marking. So.
Okay.
But sometimes the reason a skirt helps is you're obviously generating a bit of lateral resistance from the embedding it in the soils, and that gives you more capacity. Sorry?
a change in the shear plane to being fully in the soil instead of doing
Well,
the
you can't.
soil structure.
It can do that, but what you end up with doing is where did I put the cloth?
Oh, it's on the thing at the end.
All right, yeah. Hey. You've got a foundation which is skirted like that. Then you've got a passive resistance there and a potential shear plane there. If that's the load. So that it's shearing across there and you get one passive restraint there. The other option is that the passive restraint is there, and you've also got a passive restraint on that skirt.
Okay.
But you take the lower of the two, obviously you've got to calculate it both ways.
Yeah.
And that's all you do, really. There is an argument that you can take the depth of embedment as that level there. You find it tends to cut because if you do that, you've got to allow for the weight of the soil in there, so you don't actually get that much benefit from it.
Yeah. Okay.
So it's easier usually just to say it's at the seed bed and add on a little bit for that passive restraint there, if that's where it shears. And that's it. Okay?
That's really good. Thank you.
Yeah. Any questions? Just, do you know my email address, my university email address? It's just peter.allen@ncl.ac.uk. Got any questions, give me a shout. Okay. Sorry? Yeah. I haven't got any questions. Fairly descriptive. Yeah, I've had less time this year than I used to Try to have a look at the relevant section of the DMT. You've got the capital paper as well. And that's fairly good background to some of the trenching stuff. It's better than the that I mentioned for trenching. Okay, there's not much trenching. It's probably what I do. Certain surface layer pipelines I cover, I talk about at a very high level. And it's, in some ways it's more relevant. Yeah, you know, it's not really something sort of break down the natural sense of the okay. Every day.
Hey, Matthew.
Who's doing?
Serbia. Where you go? Library. You have your pay? What? You pay? And go back. Have you got tickets to Uganda? No. Okay. You should get some one. Well, J is Uganda. J-A is R. It doesn't look like. Yeah. We should go to yeah. Yeah, we don't know.
It sounds like